people that are just coming in, we're gonna practice some of this in class this afternoon. So my job is today, this is how I see my whole day occurring. I need to finish all of the discussion packets for up to chapter 3. And I think we have 2 discussion packets that have not even been started. So that will be the first thing that we're gonna get done. I don't think it's gonna occur just during the discussion, so when we come to lab, we finish that. We're gonna be drawing chairs, so the first thing that happens is draw both chair conformations of cis 1-terbutyl 2-isopropyl cyclohexane. A, determine which conformer is more stable. More stable. And then B, and I'm gonna watch you all work, name the compound. Using the latest IUPAC version of nomenclature. All right, so I want to see you work. I want to see your chairs. I want to see all that. Let me see your chairs.
Is that what you got?
I want to see chairs.
Stable.
I don't see too many chairs. Ooh, that's a beautiful chair. Wow, that's amazing. That's a great chair.
Did you?
So up and up is this. Up and up.
Okay.
So
Oh, yeah, I think that.
you have to think of that up and up or down and down. Up and up or down and down. Ooh, that's an excellent chair. That's excellent. Oh my goodness.
This is the,
Good morning.
Morning.
I saw you send me that. Can
Yeah.
I share it with everybody?
Oh, if you want to.
Okay.
Kind of helped me. I like the image of like the person. It's pretty funny.
I haven't seen it yet. I haven't seen it. It's pretty funny. Okay, I walk around the room and I see some chairs, but I don't see much of anything else.
so,
Oh, that's yours. All right, so the first thing that happens is that they want you to draw both chair conformations. They wanted it to be and cis is pointing in the same direction, okay? So cis is in the same direction, and then they want you to do a ring flip. So I'm gonna start drawing my chair down here. Okay, so I'm gonna trace my chair so that it looks like you can follow what I'm doing. And since they want this to be 1 and 2, and they want it to be cis, my options are up and up, right? So those are the only options that you have, up and up. Or if you do the ring flip, and now your chair looks like that. Okay, then the options are that you will be down and down. And I don't mind if you do it like this, even though they probably will be done in a different notation. Okay, so those are the options. So in this position, you would have somebody axial, equatorial, and now in this one, the one that was axial became equatorial, and the one that was equatorial became axial. So this is denoted like this, axial, equatorial, and then over here will be equatorial axial. To understand that I chose this carbon to be carbon number 1, okay, and I chose this one to be carbon number 2. And then over here, I chose this one to be carbon number 1 and then carbon number 2. You do not have to pick carbons 1 and 2 like I did. You can go anywhere around the ring and you can pick your 1 anywhere around the ring. The important thing is that your 2 is next to it. All right, so that's the only thing. So somebody could have started over here, or over there, over there, over there. Okay. So they want it to be terbutyl, so I can put my terbutyl over here. Terbutyl over here would look like this. That's terbutyl in a line angle. And this could be terbutyl over here in a line angle. So that's terbutyl in a line angle. Some students, bless you, some students do not like to do line angle. That's quite fine. Some students can go ahead and do this. So you can do that. That will be cleaner. Okay, this will be cleaner than putting the carbons with all the methyls. Okay, and then on carbon number 2, you're putting the isopropyl. So your isopropyl looks like that again. If we're doing line angles. Or your isopropyl can look here like this if you're going with a condensed formula like so.
Does not one of them on that axial equatorial have to be facing, would one have to be facing down?
So to be cis, they both have to be pointing in the same direction. So remember that the term was cis. So if they're cis, they have to be pointing in the same direction. It just so happened that in the positions 1, 2, the same directions are axial and equatorial, or equatorial axial if they're pointing down. Pointing up, axial equatorial, pointing down, equatorial axial. They want you to determine which conformer is more stable, okay? And again, I'm just trying to help you guys out that when you're gonna start explaining, right, when you're gonna start explaining, you wanna make sure that you do not spend unnecessary time. Like, I'm assuming that for this to be totally perfect, you would say, of the cis 1 terbutyl 2 isopropyl cyclohexane conformer, that is the most stable. So instead of going through all of that, label your chairs. Label your chairs. You can call this chair A if you want. That, I don't like that because I have A here for axial. So I'm gonna label this one as 1, and I'm gonna label this one as 2. That will make the discussion much easier of your 2 chairs, which one will be the more stable, and what is the criteria to establish which one is the more stable. Israel.
So, will number 2 be more stable?
Why would 2 be more stable?
Because-
I'm agreeing with you,
because
2 is more stable.
The terbutyl is on the equatorial, and that is the bigger group.
Okay, so when you have 2 groups, okay, and the groups are on 2 distinct different positions, axial or equatorial, you want the largest group to be in the equatorial position because
It is
it's more stable because
less
less
Torsional? No.
1. Okay, they're all torsional. Is everybody, so people say, oh, the torsional strain is less. No, the torsional strain is from going from the chair to the boat. That's torsional. Okay, when you're thinking of torsional strain, you really are looking at the conformers of cyclohexane. In a chair, that's the lowest torsional strain. You don't want to be in the boat because everybody is eclipsing one another. But the criteria is that if you have the big groups on the axial, right, you're going to have 1,3 and 1,3. Those 1,3 diaxial interactions you want to minimize because there's a lot of steric effect. So more stable because there are less 1,3 diaxial interactions. So that's the terminology that we use here. 1,3 diaxial interactions are minimized. Okay, now we want you to go ahead, is everybody? Now the next thing is they want you to go ahead and use the compound using the latest IUPAC version. My suggestion is that you do this, right? My suggestion is that you do this. Your tert-butyl, that is this. Your tert-butyl, that is this. You have your CH3, you have your CH3, you have your CH3, and that is attached somewhere as a substituted substituent. This is called what? This is your 1, 1, right? The point of attachment is here, so that's 1, and then you're trying to find the longest chain. It doesn't matter which way to go. There's 2 carbons, and on carbon 1 you have methyls. So this is called 1,1 dimethyl ethyl. Oh, there's an H there. Your isopropyl. Your isopropyl is this. You have this carbon, bless you, that has a CH3 and a hydrogen, like that. And your isopropyl, again, the point of attachment is here, and it's 1 and 2. This will be 1-methyl ethyl. And then all you're gonna do is write this all out, right? So now you wanna write it all out. And so you start over here. And again, the numbers are not going to change. So this will be your cis 1, 1, dimethyl ethyl, and then 2 parentheses, 1-methyl ethyl, close parentheses, and then cyclohexane at the end of all that. So, don't lose points for something like this. People lose points for things like this, and I want to say, well, why? So that's how you're going to go ahead and be using this, the old and the new. All right. So this is one of the techniques of using old and new. We keep moving them one to the other, and whatever. All right. There is much to do still on chapter 3. All of it will be done this afternoon, so today, at the end of today, chapter 3 will be then put aside, and all we're thinking is of chapter 4. This is a definite better room for lecture, so I'm starting chapter 4 right now. Is everybody okay? So today we're finishing chapter 3. All right, chapter 4. Okay, so far, and I'm sorry I'm even apologizing already, even though I said to the other class, I'm using the PowerPoint, and then I ended up writing everything again. But so far, for me, all that we have done is just started a little bit of introduction, and no reactions has occurred yet. Remember that chemistry is the study of matter and the changes it undergoes. Literally, we haven't seen one reaction just yet. All we did is take a trip to the past, review already. Chapter 1 was a trip to the past. In chapter 1, if I look at chapter 1, frankly, there's only one new thing in chapter 1, in my opinion. And that new thing was the major and minor resonance contributor. Everything else you had done some way, some other time. You did atomic structure, you did electronic configuration, you did electronegativity, you did polar bonds, you did resonance structures, you did Lewis structure, all that you did. The only new thing was to give it a name, from your molecular formula to the structural formula to the condensed formula to the line angle. That's new for a lot of you. Maybe in your other chem you had some, but my assumption is that that's new for any organic chemistry student. And what is new is the major and minor resonance contributor and the criteria for it. And I'm done. So nothing really chemistry-like, just intro. We got to chapter 2, and we took a look at the hybridization from our point of view. Again, you had done sp3, you had done sp2, you had done sp, you had done pi bonds, you had done sigma bonds. We're labeling them our way. Sigma carbon sp3 to carbon sp2. That's our way. That's new, right? Bond angles, all that the same. Chapter 2, I introduce all the crazy functional groups that you have to have them all memorized, obviously for this next exam. Then we came to chapter 3, and all we did was introduce structure. Structure of alkanes, their name, structure of cycloalkanes, their names. Now we're getting to the reactions of them. It's everybody there. So that's really all we've done. I'm apologizing, but I know that I'm going to switch us back and I'll start drawing again. So we're looking at this as the study of chemical reactions. I'm not going to watch you copy all of this because I have no patience for it, okay? So I'll tell you when you're going to copy. So far, I know that you know this. Everybody knows that we go from reactants to product. It hasn't changed in organic chemistry. It's still the same. In your class you balance, we don't care about balancing anything. The assumption is that we have at least Avogadro's number of reactants and Avogadro's number of products. So we do not balance in OChem at all, okay? But we do know again that there is a mechanism which is a step-by-step pathway. We want that. We want to know how this occurs. So before, when you had HCl reacting with sodium hydroxide, you didn't care how that happened. You know that they form sodium chloride? We want to know. We want to know how you got there. It's like if I know that you're going to New York City, I want to know, how did you go? Did you drive? Did you take the train? Did you fly Southwest? Was it cheaper than American Airlines? I want to know. I'm nosy. That's how organic chemists are. They're nosy. They want to know how this occurs. And then, of course, there's a little bit about thermodynamics and kinetics that you spent a whole semester with thermodynamics, it seems like. Well, I don't know if it was a whole semester, but it seemed like it was a long time. In Chem 2 that you did, I think now kinetics is in Chem 1. I don't know, I haven't taught these classes in so long. Kinetics is in Chem 1 now, right? Okay. All right, so we're all on the same page, we have no idea. All right, so let's take a look at this, and I already do not like that there. That should be a carbon there. And I already don't like this, so I'm going to go ahead and start drawing. Did you see that? I already have a problem. I don't like it all. I do not like it all. Why do I do PowerPoints, right? Just to keep us going. First of all, we're looking at the reactions of alkanes. So this is going to be reactions of alkanes. And we are going to come up with what is called a general formula. And in a general formula, my alkane can be expressed like this. So an alkane is an R group with a hydrogen. And you can imagine what this could be. This could be a methyl, an ethyl, a propyl, an isopropyl. So that's what that R is going to stand for. And I'm going to react this with a halogen. Halogens are diatomic elements. They're usually represented like that. This reaction will not occur in the dark or in the freezer. In order for this reaction to occur, you either need to apply light, UV light, or you gotta put it in the oven. Otherwise, it doesn't work. Plain English, if you don't see that, it will be no reaction. Is everybody there? We're not playing that game till Chem 4, but the option is if they don't exist, like I said, if this is in the freezer or in the dark, over here will be a no reaction. So, and what I know is that I'm going to substitute a hydrogen for a halogen, so it's seen as a substitution, and I'm going to substitute then that hydrogen for the halogen. All right, so the RH, this RH is going to represent an alkane, generic. We'll start introducing it all. Your X2 is your halogen. Oh, but wait, there are limitations. Only works, only chlorine and bromine react. Fluorine is explosive, iodine is too slow. We let it go, okay? And the RH, RX, new nomenclature is haloalkane, and this is new. Old nomenclature is alkyl halide. You have to know them both, as per usual. Remember the story, the US, this is a little bit of past for all of you. In the 1975, 76 was the famous oil embargo. I don't know if you've heard of this or whatever. And the United States wanted to switch the whole system to the metric system, you know. We use, you know, the famous English system. And at the time, in the 70s, they wanted to make the big switch. You know how far we got? The 2-liter Coke bottle. That's the only thing we're using in the metric system. Everything is a gallon of gas, is your pound of meat, is your, you know, ounces of milk or quarts or whatever. So the only thing that we were able to adopt in that transition was the metric system. So when students want to fight the old and the new, hey, it's our culture. We don't want to make any changes, so we got to know them both, okay, the old and the new. This is the mechanism, okay, so we talk about the mechanism. And the mechanism, and again, I want to show you the slides, even though you might not like it, and even though there's already that big error right there. So it requires light or heat to start the reaction. The most effective light is blue. I'm not going to remember any of that. And then many molecules are produced. So here's the steps of the mechanism. First of all, it's called a free radical chain reaction. What's a free radical? What do you know as a free radical? Unpaired electron, she says. A free radical is also can be seen as an odd electron, an odd number of electrons. So a free radical for me can be this guy. So, sorry. And I'm getting ahead of myself, but it doesn't make any sense otherwise. We have what are called homolytic cleavage. Plus, if I turn lights on and off, people wake up. All right, in a homolytic cleavage, I'm going to take this chlorine that looked like that chlorine molecule that looked like that. I had it all of its lone pairs. Right, so we have all of its lone pairs. When we're doing a homolytic cleavage, means I know that we had 2 electrons there. I'm going to get one of those, and we show it like this. We take from there and do a half-headed arrow. It's a half-headed arrow. And after that, your chlorine now looks like this, where you have your lone pairs, back again to the same thing, and now you have that odd number of electrons, odd number of electrons is called a radical. So it can be in a carbon, if your carbon looks like this. Let's say your carbon looks like this with a dot. That's a radical. Okay, that's a radical. If your oxygen looks like this, lone pairs, and a dot, that's called a radical. So you always have an odd number of electrons. Okay, odd. An on pair, and odd. Okay. If you want it balanced, you can call it a 2, but we'll destroy that soon. Okay? So we start there. Alright, so in my chain reaction, we see that the first thing that we need to do is to generate the radical intermediate. Okay, so we're going to stop at each time. The mechanism occurs in 3 distinct steps. I'm just going to say it out loud so you don't copy everything. First step is the initiation step. Second step is propagation. And the last is termination step. So there's those 3 steps. I'm going to draw because you know me. I do not like to do these things without me drawing.
Say the 3 steps.
I am going to write them. So back again with this. This is called then, the reactions of alkanes are called the free, you see why, free radical. And then it's called chain reaction. So it's free radical chain reaction is what it's called. 3 distinct steps, so your mechanism. 3 distinct steps. Step number 1 is going to be called the initiation step. We'll see what this means. This is the beginning of the formation of your radical intermediate. So how does that look to us, right? In this initiation step, right? So I'm drawing steps of the mechanism. Step 1, initiation step. This is the step that you need the light. So if we were looking at the chlorination of methane, right? Over here, if we were looking at the chlorination of methane, the first thing that I'm going to do is that I'm going to draw the chemical reaction. And I'm going to show the reaction. Your book likes to show the reaction like this, right? That's what we saw at the beginning of the lecture. We saw it begin like so, and we saw it like this, right? I don't know if you remember, but we saw this like that, and like this, and like this, and I'm going to tell you that this is too much time consuming, all right? So I'm going to use the information, the structural, and the general formula, and I'm going to say this is just not good enough for me. I know that what I'm going to do is I'm going to go ahead and replace the hydrogen with the chlorine. And I'm going to come over here and show it like that. And if this is what I'm going to do, when I'm doing the steps of the mechanism, I need to see it all. Okay, so you need to be able, when you're drawing the steps of the mechanism, one of the things that you need to do is you need to show how these 2 work form, okay? Because that's the product of reaction. So that's what you want in a mechanism. You want to see how that occurs. Okay, so my step 1, which is the initiation step. In this initiation step, I'm going to have my chlorine. Chlorines are like green. And I want to show you how sloppy OChems get to be and how sloppy you will get as well. Okay, so that's the beginning. And in that beginning step, we're showing all these lone pairs and everything else. We're cleaving the bond homolytically. So you have to come in and do the half-headed arrows. And again, this is only if they ask for you to draw the steps of the mechanism. If you do not put on this arrow light or heat, this will not occur, okay? So if you don't write light there, I'm not gonna give you all the points because it doesn't happen. Or heat, it will not happen otherwise. And now we see that we have generated 2 of these. So we have a chlorine dot, and now take a look at that. That's really all we care now. We don't care about all the other lone pairs because they're not gonna do anything, right? So it becomes very cumbersome to be doing all of these. I'm gonna write 2 here so that we follow our background of our Chem 1 and Chem 2. Oftentimes, if you don't see the 2, so I'm fine with that. Okay, now here comes step 2. Step 2 is called propagation steps. Did you see what happened in step 1? If you have to think of your other course, comparing your chemical reactions from the other class. Chemical reactions in the other class, anybody remembers how you named them? What were they? Didn't you learn them by names? Did you have like a combination reaction, a decomposition reaction, single replacement, single displacement, double displacement, neutralization, right? That stuff was from before. I see this as a decomposition reaction. You have one reactant, you're breaking into that. For us, the initiation step, you have generates the reactive intermediate. That's an intermediate, this is not a product, that's an intermediate. So you generate the radical intermediate. Radicals, I don't know if you know, but if I ever come back, I definitely, I'll step back a little bit and just give you a perspective. There are chemists working in every industry that you can imagine, okay? There are chemists working in breweries, there are chemists working in Heinz and Stouffer's and all that food that you buy that is all processed. There are food chemists that are working in that. All the chemicals that you're putting all over your body, going from shampoo to conditioner to creams, those are also cosmetic chemists, and everybody kind of gets their specialty. For a while, I lived in Pittsburgh, Pennsylvania for many years, and I taught at La Roche College, which was a private 4-year Catholic college. I thought I had died and gone to heaven. It's just like my dream come true of a place. But in between, I also wanted to work at Heinz. Heinz was a big ketchup company. Well, now that I'm getting older, I think I just want to work for Estee Lauder. I want to work in cosmetics. So I don't know where I'm going to end when I retire, but these radicals, if you watch TV, there's not one commercial that says, oh, antioxidants to combat free radicals. That's all they're talking about. They're talking about really molecules that would split into the O with a dot. And all that we're wearing, all that we're using, all that is supposedly to break that up because our bodies don't recognize these free radicals. Our bodies recognize bonds and nice molecules, they don't recognize that. So any cosmetic that you're buying that they're trying to sell it, takes away the free radicals. That's what we're talking about. For us, these free radicals are going to promote a lot of reactivity, okay? And in these propagation steps, what you really, really want to do is you want to show how these guys are going to be made. All right, so we need to show how we're going to make these in my propagation step. So, okay, I'm the reactive intermediate, and I had my compound. So I had this guy that you said I'm starting with. This was methane that she wanted to be drawn like that, because of course we're showing the steps of the mechanism. And I have chlorine that is my reactive intermediate, and I'm just going to make my drawings beautiful. Then we'll worry about the plus and everybody else. Take a look that we no longer need light on that arrow. that is done. We use that just to break the chlorine. But I wanna show how the steps are with the arrows. So I am gonna go after you, hydrogen, because you are going to split your bond also homolytically. You see that this is the generation of a bond right there? You can see that your hydrogen ended up making the bond with chlorine. One of my products was formed, right? So there's the hydrogen forming the bond with chlorine. And of course, I was only break this up because you are going to get the other electron. But again, I told you that we get sloppy, and depending on who's teaching the class, you can either have that CH3 radical, and this is me because I know what I'm doing. I like to put my dot over here because I know I'm gonna have to go after somebody. So where that radical is really not important. Some people that will draw it here, or there are some other faculty that will put it here. Really, this is not important, okay? I'm gonna put mine there because I know how I'm gonna draw, and I have my limitations of drawing. So after so many years of teaching, I know what's gonna look good on paper. How's that? I'm gonna go back now and I'm gonna squeeze the plus just like an afterthought, because you wanna know that it's reactants to product, just like we started the class with, okay? I generated one. I have to show in the propagation step how I'm gonna generate that one. So now my C3 dot, my methyl radical, this guy is gonna be called now your methyl radical, is now the reactive species. And that methyl radical over here will go after more chlorine. Here's chlorine. We'll go after more chlorine. Remember that we have Avogadro's number of these. We don't balance equations, we have Avogadro's numbers of these. So again, you go with your arrows. I'm gonna go after you because I'm gonna have you cleave. Oh, that arrow was like wrong, right? Okay. Oh, don't like my arrows so much. Ah. La-da-dee. I don't know if you, did you practice handwriting? Oh my gosh, I did so many circles in my life, no wonder my life has turned out to be just a circle. Okay, I'll do a better job. It has to be a big circle. All right, so, I'm not joking. I am not joking. All right, so here's chlorine. We'll do a better job. I'll start with the chlorine because that way I know I'm gonna do a better job. Okay, so we wanna start it like that, because it's the chlorine's electron that is gonna form the bond. So that one was kind of fun. All right, we get our arrow together, and then we have generated the CH3 Cl bond. No light here at all. The light is only in that first step. After that, you don't need any more. Okay, and then what else happens here now? What else happens here now? And you have now more chlorine radical generated, right? So this is what is called a chain reaction. Is everybody there? The whole concept of chain reaction is that once you have initiated the step and you generate the chlorine, that chlorine gets produced over and over and over again. And so for me, and I have to try to find ways that I will remember this, my propagation step, I have molecule radical, molecule radical. My propagation steps have molecule radical, molecule radical. Your book explains this into a complicated way that frankly, I don't know if I could remember this in any other way, but this is what your book continues to say. Oh yes, in that initiation step, you had the radical intermediate. Now when you get to the propagation step, the intermediate reacts with a stable molecule to produce another reactive intermediate and a product molecule. Remember, molecule radical, more than this. But then again, you learn whichever way works best for you. I would not remember this. And then the last of the step is the end, which of course is appropriate, that you would call it a termination step. And in this termination step, you end up getting rid of the reactive intermediate. So it's like now is the opposite of the initiation. In the initiation, you generated these things. I'll go back. I'm going back. Good notes. I want to have good notes. So my last step, which is the termination step. So step 3, which is your termination steps. In this step 3, we're doing the opposite of what we did here. This was seen as a decomposition. Now these guys are going to be combination. I'm going to take any free radical that stayed hanging. So any free radical that remain hanging, I'm going to bring them into the mix, right? And I'm going to come after you, and you go after me, and we're going to end up generating a stable molecule, no more, right? So no more. No more, and take a look at how your termination steps are seen over here. There's more than one termination steps. I want you to go ahead and copy them. So your termination steps appear like this, like I did there, that I took my methyl radical and my chlorine radical and I attached them. But there's more than one termination step. Take a look at all the crazy ones. That a chlorine collides with a chlorine. If a chlorine collides with a chlorine, guess what? Wow, we're generating more chlorine. Or if a methyl collides with a methyl, wow, now we end up here with ethane. Or if the chlorine or the methyl hit the wall. When you did gases in Chem 1 or Chem 2, whichever way it was, I don't know if you remember, but part of the kinetic molecular theory were that gases travel in a straight line. Do you remember that story? Oh, they travel in a straight line, so they never drink, they go straight out there. And then when they hit the container, they were called elastic collisions. You hit one another or the container and you travel in opposite direction with the same energy as the collision occurred, right? So if you came like that, you went back like that. Not the radicals. If the radical hits the wall, you're done. It's like you lost all the energy and now you're done. So it's like real chemistry. It's not this idea of this ideal gas, all right? So if you hit the wall, that's another one. I personally, this is one of my favorite. In drawing, go ahead.
You mean that it just loses momentum, but it stays a molecule later?
Right, it's done. We're done. So when my chlorine comes here and my chlorine hits the wall, I like my wall a lot. Here's my wall, whoa. And now I'm like done. I'm attached to your wall and we're done. I don't have anything else to do here. So these are the basic steps of your mechanism for your free radicals, right? So we have that. You can already imagine the amount of information that we can get here. In a typical reaction of these, you can have methane be converted into 1 chloromethane, 2 chloromethanes, 3 chloromethanes. I mean, this can continue on and on and on and on. And to separate these things, this is a gigantic nightmare. Okay, so this doesn't work a whole lot. But this is your, so what happens, right? So what happens if we are looking at more than this, right? Because this is all going to be the same. I want to take a quick look at some other stuff that you should know, right? Again, sorry, we're looking at the PowerPoint. So your PowerPoint and your chapter wants to go ahead and finish this with a little bit of a summary that your initiation step, you created the free radical, your propagations, you really are continuing generating at least a radical. You really wanna make sure that the products that you write is the information that you have been given. And how do we use this, right? How do we use this from your point of view, okay? So let me show you how I'm gonna use this, because we're gonna do some numbers shortly. So we're gonna come out here, and we're gonna ask you, draw the products generated upon addition of bromine to ethane in light. And I think the English could be done better here, but we're not gonna be worrying about the English much here right now. All right. So how are we going to translate this? A lot of what we do in organic chemistry is like, this is like a word problem, right? This is like a word problem, and you're converting this into your equation, okay? So the first thing that you need to know is they want you to draw the products, and they're saying you're gonna react bromine and ethane, and there will be light. So I'm gonna take ethane, and I'm gonna draw ethane like this, just following the same thing that I just did a minute ago. And I'm gonna react it with bromine in presence of light. What are you gonna do? What will be the products that I'm expecting you to draw here? Mhm. So you can come over here, and like we said before, the chemistry is seen as a free radical chain reaction, but it's really a substitution. You're substituting a hydrogen for a halogen, and you're substituting a halogen for a hydrogen. It's like, hello, excuse me, do-si-do, we're switching partners altogether. Bromine goes with a hydrogen, bromine goes with the alkyl. By no means, you have to draw the steps here of the mechanism, right? So all we wanted is to draw the products generated. Only if they say mechanism is that you're gonna go through all the crazy ways, okay? I have to assume that you know something, and here is the assumption of what I think you should know, okay? So, because Chem 2 is your prerequisite for this class, I'm assuming that everybody knows what equilibrium constant looks like. So if I were to present that, everybody knows that the equilibrium constant is the expression of the concentration of the products over the concentration of the reactants. That for the chlorination of methane, like we just did a minute ago, it would be that you would have the concentration of the products over the concentration of the reactants. Is everybody there? And if I were to have given you this number, what are you gonna say? Organic chemist now speaking. We're not gonna calculate it. Everybody there? I'm not calculating that number. I'm not figuring out moles. I'm not giving you concentration. All I wanna know is what does that mean to you coming into this class? Is the number big or small?
Small.
The number is quite large, by the way. It's quite large. What does that say if the number is quite large for that equation? What is that saying? Larger concentration of products. It also means that you probably have more products than reactants at equilibrium. It's favorable for us, okay? That is favorable. It's a positive, favorable contribution to the formation of products. They continue on, la la la, goes to completion, okay, so it goes to completion, you have all that there. That's all I want, okay, that's all I want. We're not gonna calculate. And then we threw in this guy, the free Gibbs energy or the free energy change, which again just means that, the energy of the product. And you know all of this, the amount of energy, and you know all of this, la-di-di-da. Okay, this is the one I need to know. If we give you a reaction with a negative delta G, then it says that it's favorable and it's spontaneous. All we're doing is qualitative information of these numbers, all right? We don't worry about how it's done. Calculated, because that's all you did in your other course. In this course, if your delta G is negative, we say it's favorable and spontaneous. Where is the other delta G? So the opposite of that, right? If the delta G is negative, then it's favorable and spontaneous. If the delta G is positive, it was then non-spontaneous, right? And not favorable, and we don't spend time with it, right? So we really don't study reactions that are there. That's the case of the iodine. It's not favorable. So, and then there was that equation, which I'm never going to spend time with, and there were factors determining, and this is what's important. I don't know if you remember the other formula for delta G, but everybody remembers the formula for delta G, that it was delta H minus T delta S, that whole thing. Okay, so that everybody remembers, I don't know why. We're gonna take a look at this from our organic chemist point of view. So we don't look at any of this, or any, oh, I did like to have, this I added, this is a new slide that I wanted you to have. So, any process with a negative, I couldn't even include the delta in there. I guess I could have copied it from the other slide. I will do that later. I was in a hurry. So any process with a negative delta G will be called spontaneous, and that process is called exergonic. And I want to include that word because I know that my dear friend Jim DeClos uses it a lot. I know he loves that. That's such a term for biologists. And since we're trying to combine both things in this class, so a negative delta G is spontaneous, and exergonic, energy is liberated, big term in biochemistry and cell biology. If the process is not spontaneous because it's a positive, it is called endergonic. And again, this is just thinking of my friend. Okay. So words that are appearing in the new versions of organic chemistry textbook. If you have the 7th edition, that term will not appear. And I think even the way this is not appearing, because he's not really big into biological backgrounds, but in all the other textbooks like Klein, that has, he's the gentleman from Johns Hopkins, he's got a medical background, that term appears, so we need to include it here. But for us, this enthalpy that we're going to look at, and really this is the one thing we spend time with, is that heat is going to be released or absorbed during a chemical reaction. And we know that. We know that if you're going to go ahead and liberate heat, that is exothermic. So exothermic was that term, is the delta H was negative. And that endothermic is that delta H was positive or heat was absorbed. And you know all of this. So far, this is all tremendous review until we get to this next slide. I think it is the next slide. Oh no. Oh no. Okay, for us, our reactions are going to favor products that have low enthalpy or strongest bonds. I'm going to put you in the dark here for a minute. I'm going to put you in the dark because I'm not going to let you copy things that I don't need. I got to where I need to be. This is where we need to be. For so far of this chapter, the only thing that I'm interested in is these called bond dissociation enthalpies. In the word of acronyms, they're called now the BDEs. You know the story, you get to a hospital, you better know where you're going. You're going to CCI, ICU, NCIU, I don't know how many acronyms there are. These are our BDs, bond dissociation enthalpies. We're gonna take this, to break bonds, you need to add energy. To break bonds, you need to add energy. So bond dissociation requires energy, and to form bonds, energy is released. So energy is released when you form bonds, you have to apply bonds to have it happen. And this BDE can be used kind of like a delta H. It can be used to estimate the delta H. You forget that. Forget that. All right, so let me show you how we're gonna go ahead and do this. I don't know if you remember that we had this reaction at the very bottom. All right, so we have had all of these reactions at the very bottom. I'm gonna show you how simple organic chemists play the game. Okay? Yes?
I always been confused why, when two species bond, it releases energy just because it's stable.
Right.
You can't bond with other things.
Well, these things are very reactive. So to have them like that, we have to supply energy to break them. They don't like to be like that. So you have to apply lots of energy to break them. They're reactive when they come together. They, come together, they share the orbital, energy is released in doing that. Right, you're welcome. So let's take a look at the chlorination of methane. We said that it went to completion, right? The slide on the K of equilibrium said it went to completion. I'm gonna show you how we super simplify this. Then we get sloppy. You know why we're getting sloppy? Because what are we doing here? Chlorination of methane. Calculate the BDE. So then we kind of get very sloppy. We don't need to put light on there. And there is this table that is given to you. And this beautiful table that is given to you, all I'm gonna do is this, okay? Parentheses, to break a methyl hydrogen bond in kilojoules, 435. So I write my 435. And then I'm gonna add, to break a chlorine-chlorine bond, 242. So I'll put my 242 there. And then from that, I'm going to subtract to form a methyl chloride bond, 351, and to form an HCl bond is 431. So all I did was add all those numbers, okay? Using my calculator, since I don't want to be a fool in front of you, 435, I don't see anything, 435 plus 242, so this is 677, and then my 351, I cannot even use a calculator anymore, 782, so now this BDE is negative 105 kilojoules per mole. And this is how we do our bond dissociation energy. Okay, this is how we calculate it. Don't extrapolate to the way that you do things. But this is how we see this. In order for me to break a carbon on a methyl to a hydrogen, I have to supply 435 kilojoules to break it. But 351 calories are released when we put them back together again. So these are bonds broken minus bonds formed. That's how we see the bond dissociation energy. Bonds broken Okay, so over here, these bonds were broken, so bonds broken minus the energy of the bonds formed. Understanding that in order to do, those 435 were kilojoules that were added to that molecule in order to break it, okay? And the same thing with the chlorine, we had to supply that molecule with 242 kilojoules in order to make it. But the overall answer, this negative contribution for us, it's a favorable favorable, what did I say? I forget what the word I was doing. So it's a negative value, it will be an exothermic reaction. So this is seen as exothermic reaction. In that exothermic reaction, the expectation was that with a gigantic, large K of equilibrium, right, a big K of equilibrium, with a large bond dissociation energy, the expectation is that this reaction is doable. It happens all the time because there are numbers that will have evidence of that. Is everybody okay? It's gonna get much harder than this because this is too easy, okay? Yes, we have numbers to do bonds to primary carbons, bonds to secondary carbons, bonds to tertiary carbons. Take a look at these numbers for a minute, okay? So, I want to make this more complicated, okay? I want to make this more complicated. If we ask for the bromination of propane, okay? So let's ask you to draw products. For the bromination of propane. Well, what would you draw here? What are you gonna draw here when you ask this? Did anybody write anything? Nobody did anything? You were just all waiting for me? Okay. Okay, so Arian says, okay, well, I follow your lead, and I went ahead and I did this, just like you did before. So I went ahead and I did that. And I even went ahead and I did this light, right? And so she said, I really was just copying everything you did. That seemed to be right. But is that your only option? Is everybody seeing that? Somebody in the back, I think it was Kenny, that said, I'm not gonna do that. What if I say, what if I did that? Is that also a possibility? And I'm gonna say, absolutely, we didn't do equivalent hydrogens for nothing, right? Let me give you some numbers for you. Can I write you a list of numbers for you? Okay, and these are BDEs. You're gonna tell me something after that. These are BDEs. A BRBR is 192. An HBr is 368. It's 410. 397. Okay, this one. Is 285. Okay, you answer my question here, please. This one? That number can't be right. I don't think this number can be right. I don't think that number can be right. On this table. All right, let's assume it is. Does everybody understand what I want to do, or? Yeah? Yeah? All right, so let's do the one above. I'm gonna go in blue over here. So I'm saying it's gonna take 410 and 192, and then over here, 285 plus 368. Yeah? Oh, sorry. So sorry. Is everybody with me, maybe? What's happening? The 410 is to break a carbon-hydrogen bond from a primary. Oh, it should be a plus, yes, sorry. Got it, I'm like, what are they, what is the problem? Got it, sorry. So this is 602 here. Okay, this is 653. So the overall here, the BDE is gonna be, so this number is negative 51 kilojoules per mole. Okay, I'm gonna make this highlighted, like that. Let's see what's going to happen with the other one. With the other one, it's going to take 397 to break a secondary carbon-hydrogen bond. It's still the same amount for, so all these numbers are appearing the same, right? 97 plus 192, this is 589 down here. 285. So this BDE is coming out to be minus 64, again kilojoules per mole, okay, to do that one. And so how does that translate to you? What? Is everybody seeing, when you're comparing, you know, the one here that is producing 51 kilojoules or the one that is producing 64, we're turning that around and say that your secondary carbon was going to have a more stable radical intermediate because the negative value is the more favorable product that you're going to expect to have, you know. All right. Well, we run out of time. I see that we're running out of time. I have to go by my office and get a lot of stuff for